Yeah, thank you very much for the intro, and thanks a lot for inviting me. It's quite excited to be here, and it's a pleasure to have to be here. So yeah, so the topic of my talk is related to what I've been working on for most of my work, which is high-level concurrency libraries, but of course in the context of Scala. And so just to give you some context, essentially in the last 10 years, I've developed or collaborated on a variety of concurrency libraries for Scala. Some of them are actually in wide industrial use. So there's a need for production-ready implementations and so forth, and a lot of engineering work, of course, associated to that as well. Some other libraries are more experimental. It's more, more research prototypes. And sort of throughout this work, right, one common theme was actually to look at the expressiveness of approaches that can be implemented as libraries, right? Because after all, the Scala project is actually designed to be, well, one of the motivations behind the design of Scala is to enable very powerful and flexible libraries. And I'm actually going to go into more detail later, right? But what's really interesting is that work on high-level concurrency libraries is essentially work on domain-specific languages and how to embed them into host languages, right? And I should also mention a couple of disclaimers. So first of all, I'm actually not an IDE expert, right? So there's a lot of things that I'm actually not aware of, right? That you can tell me, and and the second disclaimer is that, of course, what I'm talking about here is biased also towards certain languages and runtimes, right? So my background is in statically typed languages like Scala and also Java, because these languages actually share quite a few aspects, especially if you look at the runtimes on which they run, which is the JVM. So that's, of course, another thing to keep in mind, that this is a lot of this has to do also with the fact that we're running on a JVM, but that's not a very exotic thing. Right, so what is this experience based upon, right? So there's a bunch of libraries shown here. So one is the actor framework for Scala that was first released in 2006. Then 2008, I released a library for join calculus style synchronization. That was more of a research prototype, but has actually been influential in various ways as well. Then 2012, we released the futures library for Scala. And that's, I think it's fair to say that most production systems in Scala actually use futures in one way or another. Well, this doesn't end here. We have flow pools, which is data flow, abstractions for data flow programming, deterministic data flow programming. Scala async is actually a macro library for simplifying asynchronous programming based on. So if you already use futures and promises, then Scala async can actually simplify your code quite a bit, because it can essentially, it lets you avoid programming in a continuation passing style, essentially, right? Now this system here is actually kind of difficult to say that this is a pure library approach, because this is a macro library, which means that there's the majority of, or pretty much everything that async does happens at compile time. So we're actually transforming code blocks at compile time, and so what we're actually providing here in this macro library is essentially another compiler phase, but packaged in a way that looks like a library, right? So it's not really fair to include this as a library, I would say. But what's really interesting is that sort of, well, I actually have a summary also where they were used. So these systems were actually real and were actually powering some big systems. So for example, actors were used in production at Twitter from 2008, also at The Guardian and several others. So they had to actually do some real work here. And well, as I mentioned, futures. So for example, LinkedIn's website, well, crucially relies on them. Couldn't work otherwise. Scala async is also actually in production use. So just the other day I saw actually a job advertisement from Morgan Stanley which mentioned that they're building a system on top of that. So, you know, it's clearly used in production there. And what I think is sort of interesting about this project is that what we're actually doing is sort of exploring Scala as a growable language, right? The question is like, how can we grow the language to fit our needs or to support the abstractions? And if you haven't seen it, I encourage you to watch Guy Steele's ETX Keynote from '98, which is actually on YouTube, so it's very easy to find. And right, so now of course one question is, you know, why are we actually interested in growable languages for concurrency, right? Wouldn't it be easier to just like, you know, pick a couple of abstractions and build them into the language, right? And well, if you look at the landscape of concurrent programming models and systems, then what you very quickly realize is just the fact that there are so many different abstractions and programming models, right? So we have, you know, actors, agents, communicating event loops, and so forth. Sort of one family of abstractions. We have concurrent ML, both, you know, synchronous, asynchronous, and so forth. Futures and promises, async await, async finish from X10 and Habanero Java, Habanero Scala, and so forth, right? But then also reactive extensions, which, you know, systems at Netflix are heavily using, right? Joint calculus style, coordination, STM, and many more, right? So the question is really sort of, you know, which one is going to win in the end, right? We don't know, I don't think, right? It's like at this point, it's not so clear whether we should really pick a couple of those and then just like build them into our languages. That could be tricky, right? At one point in time, STM was, you know, the poster child of, you know, a model that would solve all concurrency problems, but looking back, it's also clear that you know, that there's no widely used system that has sort of adopted STM as their principal concurrency coordination mechanism, right? So it's easy to kind of pick one and then perhaps later on wish to do something else. Okay? Now, of course, growable language also has other advantages, right? So for example, we can combine several high-level libraries embedded in the same host language. So we just get a much richer programming system, right? And in fact, there was an eCube paper from 2 years ago which looked at Scala actor-based programs, right? And looked at sort of empirically, you know, are there any other concurrency abstractions that are used together with actors? And in fact, yes, you know, futures and even sort of more low-level threat pools and so on, like they're all actually typically used together in the same software system, right? So we want to support richer programming systems, right? But on the other hand, if we can embed these models into the same host language, well, that's actually nice because we can reuse, you all the tools, compilers, IDEs, and so on for the host language, right? And that's very good, but of course it still poses a lot of challenges, and that's actually what my talk is going to be about, right? But just to mention some other advantages, right, is actually that growable languages can simplify research, right? They can be a really nice research platform because, well, developing a library extension is much less effort than developing a language extension, right? Performance comparisons can be much more meaningful because we can vary the differences in a more fine-grained way, and actually we can evaluate new ideas on real code. Okay, but now let's focus on tools, right? Because there's a number of challenges, but also I think really interesting opportunities, right? That we actually haven't really looked at. If we did, you should tell me, right? But one interesting aspect I think is that languages like Scala, which are not that old, right? Compared to Java, Scala is a significantly younger language, right? So the API designs that people come up with are, we haven't really seen before, right? So Scala has, integrates different features in unique ways, right? So for example, objects and functions are two sides of the same coin, essentially, in Scala, right? That's one of the main ideas behind Scala, is that we shouldn't distinguish objects and functions in the same way that, for example, Java does it, or other languages that have both. Of course, Scala has also, traits that allow you to compose programs in interesting ways. It has things like path-dependent types and so forth. And it has very interesting features for extending the language as well. So if you look at pattern matching, which of course is by itself interesting, but in Scala it's actually extensible using extractors. And that enables entirely new API designs. And in fact, one of the concurrency libraries I mentioned earlier, I'm going to get back to that, Scala joins, actually crucially relies on extractors to provide the API, right? And then we have things like implicits, which of course I don't expect you to know anything about. I'm going to give you a rough overview later on. But all these things essentially mean that you can design APIs that you could not design in other languages, right? But of course that holds the other way around. If you design a new library, for Rust, it's going to look very different from a Java API, right? So that's clear. But sort of the important point here is, right, is that not all API designs are actually well supported by tools, right? And that's actually one of the core issues we have, is that the tooling we have for, let's say, Java, right, but also for Scala, right, it supports certain things well, but not necessarily some new API designs that we come up with, right? And the question is, what can we do about this, right? So let me give you an example to be slightly more concrete. So actors, for example, are quite widely used abstractions for concurrency in Scala, right? What is an actor? Well, it's simply a concurrent process that communicates with other actors using asynchronous messages, right? So what does that mean? Well, if I have two actors running concurrently, then if one actor sends an asynchronous message, it means it does not wait for the receiver to receive or process that message, right? The message is simply put into a mailbox of incoming messages of the receiver, okay? And the receiver will then sort of process its inbox, essentially, right? you don't have to know a lot of details of this model for the purposes of what I'm going to talk about next. But essentially we have this asynchronous send operation and of course a corresponding receive operation, which is event-based in the sense that an actor that waits to receive a message is essentially suspended and inactive, right? And sort of with an event-based mechanism, as soon as there's a message that the actor can process, well, it will it will react to that incoming message, right, in an event-based way. I'm going to show you a small example in a second. What's interesting about this model is that it's actually rather easy to avoid data races. And that's not actually fully enforced by the language or type system, right? But that's actually also relies on convention. But it's a very simple convention. So, for example, if you have actors that exchange only immutable objects, right? Well, then they're not going to share any state, and there won't be any data races, right? Of course, you also have to make sure, once you create actors, that they don't capture any immutable state either, right? But these are conventions that are relatively easy to follow, and then the nice thing is you don't have any issues with data races. Yeah? So that's, of course, a nice thing about this model. However, if you look at the more complex messaging protocols that we built using actors, right? Then actually this becomes much more difficult, right? Because we have to verify that all the messages that are being sent around, follow the correct protocol and so forth. And that's actually where things get tricky, and also where the programming model doesn't really, help you with anything, right? So let me give you a very small example. So here's a simple actor called task coordinator, and essentially this is a simple class, right? Class declaration here extends some library provided trait in this case, which is essentially an abstract class, right? In some ways, slightly different, but the important bit is that this actor, right? It has a field that can point to an optional actor ref. An actor ref is simply a reference to some other actor, right? Initially here the option is none. And well, here we simply define the behavior of this actor. And the behavior says, well, in the case when the actor receives a start message, which contains a reference to a worker actor, well, then we're just going to initialize our field, okay? So then this field is now a non-empty option, right? In a second case where we receive a do message, and the do message now contains a collection of tasks that should be performed, right? In that case, well, of course, we want our worker to perform these tasks. And so we want to assert that our worker field is non-empty, right? Should be a non-empty option. Now, of course, there can be an issue if, or this assertion fails, if we have a client that sends a do message without a prior start message, right? Because, well, the worker is not yet initialized, and that will make the assertion fail. Now, if you want to debug this kind of program, right, and you're at the point where this assertion has failed, of course you want to know what led up to this point, right? What happened in the past that caused this problem, right? So you want to find out, well, where's the client and what did the client do, right? Like, why did the client send a do message without sending a start message before, right? So we basically want to find out the point in the program where the do message was sent, right? That's a natural thing to do, right? So that we can trace back the chain of events that caused our assertion to fail. Now the problem is that the sender and the receiver are executing on different threads, in general. Actually, in the runtime system, sometimes they can actually be executed on the same thread, but that's rarely happening, or in general, it's not going to happen. So they may be executing on different worker threads, on different stacks, right? And well, of course, the message is not transferred through the stack, but through a concurrent queue, right? So it's actually not easy to trace the flow of control using traditional stack-based debuggers, right? They just don't work anymore in this context, right? So so there is actually an interesting solution to that, and that's called stack retention. So what we can do is, at the point when a message is sent, we actually save the call stack at that point, including information such as values of local variables and so on, typical information associated with stack frames. Then we attach the call stack and all this information to the object that we're sending, right? Of course, that only happens when we're debugging our program, right? And then, of course, when we reach a breakpoint in the receiver, well, we can present all the collected information, right? Because we have reference to the message that we've received, so we can look at all the associated information, right? So that's actually really helpful. And in the context of Scala, actually, Julian Dragos from TypeSafe presented ideas on this at the Scala workshop a couple of years ago. And this system actually also works for futures, right? So what you can do is, with a future, don't worry if you're not that familiar with futures, but what you do is you basically create a computation that runs asynchronously with the creator of the future. And asynchronously, this future object is completed with the computed result, right? And then you can actually, you have combinators that can transform futures into new futures, right? So the transformed future is completed at the point when the first future, FUT here, is completed with a value, and in which case we take the value and transform it, right? And the transformed result is then put into the transformed future, right? And of course that happens also asynchronously, right? There's no waiting happening here. We just do things in an event-driven way, right? And then finally we can register a callback, for example, right? We could say, well, as soon as the transformed future is completed, we can handle success and failure, right? Now, of course, the issue is that, again, if we want to step through our program because there's an issue, right? For example, we get a failure here that we don't expect, then we can, again, find out about the context at the point when the future was created, right? So again, we can use a similar scheme of stack retention as before. Okay. So now, of course, you might ask, well, are we done, right? Because that we've seemed to have solved one of the main issues, right, with concurrent code and debuggers, right? So well, of course, one of the issues is that we may have support for actors and futures, and in fact, for Scala, just 2 months ago, the Scala IDE for Eclipse actually shipped with an async debugger that allows you to do exactly that. But these are maybe not the only abstractions that we want to support, right? What about some interesting new abstractions that we're experimenting with, or that are not as widely used yet, right? What do we do then, right? So, like for example, streams. I mean, streams is something that's is just becoming more and more important and widely used, right? But there's not really any good in this case, debugger support and so on, right? But then also data flow, abstractions, drawing patterns, and so forth, right? And of course, the effort to implement support for a concurrency abstraction is quite high. So if you look at the timeline here, actors were first released in 2006. 2008 they were used on a larger scale than the ACA framework, which is essentially the successor actor framework, which is much has many more features also in terms of distribution. Was released in 2009, right? And then sort of 2013 we have Julian Dragos, and then, well, actually when these things were released in executable form was 2015. So, there's essentially, 9 years to go from, releasing a concurrency library to having good debugger support, right? And that's maybe a little too much, right? We don't want to wait 9 years every time we come up with a new concurrency library, right? So what can we do about this, right? And I think that there are 3 issues that we would be good to overcome to actually improve the situation here, right? And the first issue is that, well, what is a concurrency library in essence, right? In essence, it allows me to express control flow in a new way, right? To express and compose and coordinate control flow, right? So we have new control flow abstractions, right? And these may not be the same as what we're used to, right? We're not just running on a single thread, right? And we're maybe not even just doing simple synchronization between threads, right? It may be much more complex, right? And the second issue, I think, is that the development of tool support is completely decoupled from implementing the actual concurrency libraries, right? There's no interface, which means that someone who is interested in developing good tool support, they have to essentially reverse engineer, the target concurrency library, and that's of course not a very efficient way to develop things, right? And the third issue, I think, is that, which is kind of unfortunate, is that, well, given that the development effort is so high, well, only for a few libraries that are widely used, people will actually go through the to the effort to actually implement good tool support. Yeah. So what about issue 1? The fact that concurrency libraries offer new ways to express and compose control flow. What can we do about that, right? And well, of course, typically the control flow that we're expressing spans several threads, right? Otherwise, we wouldn't have real parallelism and so forth, right? We're not only interested in sort of single-threaded code. Well-known examples, well, actor multiplexing, where actors are multiplexed onto thread pools. Futures are also scheduled to run on thread pools and so forth, right? And of course, the control flow abstractions, they're not necessarily implemented in terms of abstractions that are well supported, right? And I'm going to show you an example in a minute. And in fact, the very nature of these concurrency libraries makes it so that you never express a new concurrency abstractions in terms of an existing one, right? And the reason is simply efficiency and scalability. So for example, let's say we have good tool support for futures, right? Let's say I come up with a new abstraction, let's say for stream processing, right? Then the mere fact that I want to use my streaming abstraction for video streaming at Netflix means I'm not going to implement it in terms of futures because of the extreme requirements in terms of efficiency and scalability. So that means, well, I can't just piggyback on good tool support for futures, right, for example. So that's in the very nature of these libraries. Okay, so, or let me give me a more extreme example. So as I mentioned, in 2008, I released this joins library, right? And it's actually quite interesting. So what you can do is you can express essentially synchronization constraints using join patterns. And what happens here is, well, we're declaring a class that inherits from some library provided class here. We declare, well, so-called events. These are singleton objects. So in Scala, singleton objects are built into the language, and they actually have corresponding singleton types. So it's actually a very sort of first-class concept in Scala, right? And these singleton objects, read and write, they are, well, they're events. So we can essentially invoke them to read and write from this synchronous channel. Okay, so I'm just going to give you some high-level intuition about this, right? So what we do here is we declare a join pattern, which says, well, if you have an invocation of the read event and also an invocation of the write event with argument x, well, then you can actually reply to the read event with x, right? Because the guy who reads wants to read x, and we can reply to the write event with unit, so that the writer actually just completes, right? So that's why it's a synchronous channel, because both the reader and the writer will wait until the operation is completed. Yeah, both the reader and the writer. Okay, so this is a sort of high-level way to specify these synchronization constraints, right? And now, what's interesting is that, well, these events, like x, for example, this argument, this is actually not transferred from the writer to the reader using futures or actors, right? This is using a completely different mechanism. So, you know, if I want to use this async debugger, it has no idea what's happening behind the scenes, right? So it's not going to be, the async debugger is not going to be very helpful to debug code like this, okay? Let's have a look at issue 2, right? That the fact that when we implement tool support like debuggers, they're completely decoupled from the library implementations. And that's kind of a pity because, well, it's actually the library implementer who's most familiar with the underlying mechanics. And actually, let me just go back to this example. The logic that does the matching, right, that finds out whether there's an event on both of these events, where there's an invocation of both of these events, is actually is rather involved, right? The user doesn't see any of that. For the user, it's just a high-level synchronization constraint, basically. But in the implementation, we actually leverage this way of extending pattern matching in Scala. So the pattern matching here is completely replaced with custom logic of the library, right? I'm not going to show you how this works, but if you're interested, you can actually look at our paper on this. And actually, Scala is not the only language that allows this kind of customization. For example, F# also allows you to extend pattern matching in quite involved ways. Okay, so the library implementer is actually familiar with the mechanics of how this coordination and so on works. But there's, as it stands, right, there's not really a good way for the library implementer to give hints to the tools, essentially, right? And I think that it could be different. And I can actually show you an example from a slightly different problem where tool support can actually be provided to some extent by the library itself. Okay, but sort of the bottom line is that, well, as a tool developer, I have to sort of reverse engineer the library implementation, right? And when people worked on the async debugger, when Julian Dragos worked on the first prototype of the async debugger, well, of course, he had to talk to me, for example, people like me who know how futures and actors are implemented, right? And so on. Luckily, we were sharing an office at that time, right? But it's not always the case, right? So, yeah, that's a big issue. Now, what's really amazing is, perhaps it's not amazing, but what's really interesting is that we can actually equip libraries in a way that really improves their usability and also ability for tools to kind of know what's going on. And I'm going to show you some examples. So for futures in Scala, we actually tried to make them both very flexible so that they could actually satisfy a lot of requirements and use cases, right? Because we had actually, when we worked on futures, there were I don't know, between 5 and 7 different futures libraries for Scala, right? That all had different features and whatnot, right? And we wanted to consolidate all of that in one library that was flexible to cover all these use cases, right? But at the same time, we wanted to make sure that it's highly usable for also people that are not intimately familiar with, that are not concurrency experts. Yeah? So for example, if you write a Play web application, you're going to have to use futures, right? Every user of the Play web framework must use futures essentially. But this Play web framework is actually designed to be extremely easy to use, and it is actually, right? But that also, of course, requires that we can use futures in a way that's very easy, right? And the example that I'm going to show you should also show that with only little implementation effort, the usability of libraries can be improved drastically, right? So if you look at, this is an interpreter session. Actually, I should have probably shown this in our worksheet in Eclipse, but this would look essentially, very similar. But what we do here is, essentially the simplest possible future using program, right? So we import the members of the Scala concurrent package, and then we create a new future which computes an important result, right? But if you do that, then you'll actually get a compilation error which says cannot find an implicit execution context, right? And of course, if you read that, you'll think, well, what does that mean? What is an execution context? Why is it implicit? And why why do I need that, right? So it's to a beginning programmer, that's not very useful, right? If you're not a Scala expert, you don't know what's going on. But we have, it continues, right? It says you might pass, this parameter to your method, or you could also import this execution context .implicits.global, right? And in fact, you can actually just copy and paste this line, this import, put it at the top of your, top level of your file, and that will actually make the program run as expected, right? So in a sense, this message is very helpful to, as sort of a quick fix, right, of your code. So that's actually very nice that you get this extra information. Now the question is, how do you get this, right? And let me just show you how this works. It's not going to be very complicated. So what we do here is when we create a future, this is actually rewritten to an invocation of the apply method on the future singleton object, right? And this block of code here, well, that's passed in as an argument to the apply method. Okay, so the future singleton object looks like this, right? There's a lot of comment here, and then we have this apply method, right, that we're invoking. This apply method is a type parameter. It's not so interesting, but the sort of this block of code is the body here, right? And this type arrow t, right, means that this is actually a by name argument. So we're not evaluating this block of code at the point like before we call the method. By name means that this expression is only evaluated when it's actually used within the implementation of the method, right? So it's on-demand evaluation, essentially, right? Of course, this wouldn't make sense if we would evaluate this block of code beforehand, right? Because the whole point of futures is that we asynchronously execute this, right? So that's why this is a by name parameter, okay? But this can be any expression or block that computes a value of type t, right? Okay, so far so good. The second parameter list, actually, right, is now this execution context, which is marked as implicit, okay? And what this means is, so this implicit keyword, right, means that the user does not have to pass an argument explicitly, right? So we don't have to pass in something here. All we need is that there is a value of this type execution context in scope, right? And it's marked implicit, okay? So for example, up here, right, let's say if we had, of course, an import that imports some execution context, and that is also marked as implicit, well, the compiler would automatically pass it here as the implicit argument. Yeah, makes sense so far? Okay, right, so it's actually not that complicated, right? I mean, there are rules, of course, to kind of be more precise about which implicit value should be picked and so on, right? But sort of the rough idea is not that complicated. Okay, so this is this implicit execution context, and of course, what it means is, this is actually a thread pool that runs the code that's provided here, right? And also when we provide other closures that we pass to futures, right? Then those closures will also be executed on the whatever execution context is available there. Okay. Now the interesting bit comes now, right? It's actually declaration of execution context of this type here, which is a trait here in Scala. You can think of this as just being essentially an interface, yeah? With a bit more flexibility, but it's essentially an interface here. And well, the important bit is actually this annotation, right? So the annotation says, well, at implicit not found, right? And then we have this message that we've seen before, right? And so what this annotation means is that, well, if we have a compilation error because an implicit could not be found, an implicit of this type could not be found, well, then please, show this error message, right? That's all it is, right? But it's really cool because, as the library author, the author of this code, it's very easy to just add this extra annotation, right? There's not a lot of effort, but it'll help many users, quite effectively, right? And what's actually interesting, and that's actually currently not done, but is something that I think would be quite reasonable, is to actually let the IDE, turn this into a quick fix, right? Because, for example, you could just add this import to, at the top level, or at some enclosing scope that's reasonable, right? And that would quickly fix your problem, right? If you're not interested in a quick fix, then you're probably know more and can fix it in different ways yourself, right? But this is actually kind of interesting, right? So this is, this is a very modest example, right? But this is actually communicating something from the library to the compiler, right? And of course, you see the same error message also in the IDE, right? So that thing I found quite interesting. And now, actually, you can actually go further, right? And here's a small proposal, right? Which is because we had this whole problem of control flow, right? That different libraries provide new ways of defining control flow, right? And what if our libraries could explain the control flow to the tools, right? Or in a way that it can be understood by tools. So what I mean by that is that as a library implementer, why not add annotations or hints that can tell my async debugger, right, where to save context information, right, the call stack of the at the invocation site, right, and I can also include information about where this context information should be attached to, right, and then of course my tools they could extract these annotations and can show me library specific ways to explore this control flow. Okay, so here's an example, right? So let's say in my future we've already seen this singleton object, right, where I have my apply method, where I cut out all the comment here. I could, for example, provide an annotation. I don't know, async save context, right? Naming is difficult, but something along those lines, right? And well, what would this mean, right? Well, this could mean, please, if you're at an invocation side of this method, right? That's a point where we actually create a new feature from this block of code, right? At this point, well, please save the context. Of course, whatever the context is, but typically it's the call stack plus stack frame information, values of local variables, and so forth, right? And now, of course, we have to say where we want to attach this information to. And well, in this case, of course, we want to attach it to the object that's returned by this method, right? By the newly created feature. This could be a convention, right? To say, well, if I don't specify anything, you just attach the context information to the object that's returned from the method, right? And so if you have a different example, which is the case where we have actors exchanging messages, right? In this case, we have to look at the place where messages are sent, right? Where if the asynchronous message sends. And in this case, this is using the akka actor framework, where to interact with an actor, I need to use an actor ref. Okay, so that's just a simple, a reference to an actor. Okay, and this actor ref has methods to send messages to the target actor. So behind this actor ref, there is an instance of a subclass of actor, which contains the actual behavior of the actor, which is what we've seen before, right? But this is the interface that clients use, right? They use an actor ref and then invoke methods like tell, for example, right? Which is an asynchronous message send. And again, here we could say, well, at the invocation site of this method, well, please save the context. But in this case, you want to attach the context to the message object, right? The argument actually here, right? Not the object that's returned, because it doesn't return anything. Unit is void in Java essentially, right? So we have to attach it to the message because that's what the receiver receives. Okay, so I mean it's not that difficult to specify that, right? And that way, the author of the library can directly provide this information, right? Right. So I mean, the advantages of these kinds of approaches, right, similar to this implicit not found, is that, well, the implementation effort is very low, right? But we have some way of getting into the brain of the library designer, so to speak, right? Leverage the knowledge here. And the payoff can potentially be quite high, right? Of course, what I presented is extremely limited, right? This is just a thought, right? This is nothing that's developed or anything. But along those lines, I think this could be quite interesting to explore. But of course, there are many more challenges, right? So for example, if you think about the meaning of things like step over, right? And so forth, right? Then the problem is, well, once I have these steps, they lose their meaning once these steps cross thread boundaries, right? Because they're inherently stack-based, right? So different concurrency libraries, right? They may have different interpretations of what is a useful step, right? So for example, if I think of message send with actors, well, what's well, it's maybe not the best example. A better example would be in the joins example, where a step into, I don't want to step into some random implementation detail, right, and so forth. So there should be some way to customize these, the meaning of these things, right? And also that's related to the atomicity of library abstractions. So if I have, for example, if my concurrency abstractions is organized in a way where I have methods that are atomic, well, that's great because, well, I can just step over a method invocation and I'm and that's fine, right? So for example, a concurrent hash map, that's no problem. But if I have a different abstraction where the granularity of atomicity is not simply the boundaries of a method, well, what do I do, right? Then I don't really have good support for that, right? So what I mean here is I want to do an atomic action, whatever that means for this library, right? And this atomic action may not be available as one atomic method call, right? And finally, that's another thing I want to talk about a little bit more, is when we combine concurrency abstractions, we run into issues, and I think tools could actually help with some of these issues. Okay, so what's the problem? Well, actually I mentioned this at the beginning of my talk. To some extent it's good if we can combine different programming models and abstractions in the same program, right? It can be quite natural. For example, actors and futures have a very nice integration where you can actually do an asynchronous message send, and when you want to wait for a response, you can receive the response as the completion of a future. Yeah, so that's a very natural way to get request response patterns in an asynchronous setting, right? But it doesn't matter if this is natural or not, right? Because as seen in this empirical study from 2 years ago at eCube, developers will do it anyway. So there has to be some way of abstractions to play reasonably nicely together. And in fact, if you look at libraries like Java util concurrent, well, they're actually more like toolboxes, right, with several concurrency tools that you might want to combine in different ways. Of course, this all results in challenges, and they have, of course, implications for tools as well. So let's have a look at a more concrete example here, which is actually in the Scala world is extremely common. So, for example, again, this is a simple actor, similar to what we've seen before, right? So we have an actor that has workers in this case, and again, it can receive a do message containing a collection of tasks. And the idea is that, well, in this case, we have a collection of workers, so we can send each worker, we can send a task, okay? So if you're not familiar with zip, no worries. So like zip simply takes these two collections and returns a collection of pairs, right? It returns a collection of pairs where each pair has a task and a worker. And then we simply convert this collection of pairs to, well, actually a collection of futures, okay? And this is what I've mentioned before as an asynchronous message send, where we send a task to a worker, and but we're actually expecting a response. And now this is a future, and this future will asynchronously be completed with the response that the worker sends back, right, when the worker is done processing the task. Okay? So we actually get back a collection of futures here. Does this make sense? Roughly, okay. Right, so it's not that important. So we have a collection of futures here, right? And now we can actually create another future called all done, which is completed once all these futures here in this collection requests are completed, okay? And this future then contains a collection of results, okay? And well, what we want to do is once this future is completed, you know, when this is complete, then we want to send our collection to the sender, and that's the sender of this do message, right? Because we've received a do message, and well, whoever sent us this message would like to receive the overall, you know, result of processing all these tasks. So we want to send it back to the sender, right? And sender always returns the sender of the current message, right? Now, the only problem with this code is that there is actually a race condition in here, because let's say this actor receives a do message, right? And it kicks off these computations here, sending tasks to workers. And in the meantime, while all these workers are processing these tasks, there's a second client coming along sending another do message, right? Well, then, of course, the sender is no longer the first client, but it's actually the second client. So that means at the point when this all done future is completed, sender might now point to the second client, right? And I would send the results from my first do message, I would send to the second client, right? Of course, that's not very good. So we have a problem here, right? And how can we solve that problem? Well, we can simply make sure that we make sure that the actor that we respond to is fixed, right? So we first have to find out who is the sender and store that somewhere so that this never changes again, right? And once everything is done, we can send the result to the correct client, right? So the fix is not that difficult in a sense, right? And so, well, the question is, you know, can tools help me with issues like that, right? There's a lot of work on systems like find bugs and whatnot, right? And I mean, essentially, you want to find more of these issues, right? Because debugging such a thing, especially if it's a race condition, right, can take you can spend a lot of time trying to debug these things, even though the actual fix might be relatively simple. Okay. Good. There's actually an alternative, or an approach that's related to this problem, which is called Spores, which is one of our recent projects. And Spores are essentially refinements of closures that demand an explicit environment. I'm going to show you an example in a minute, but essentially we can constrain the variables that are captured also. Like we can have type-based constraints on captured variables. Okay, so details are all in this EQ paper from last year. But essentially, the way we can fix this previous problem is to say, well, for our all done future, instead of just passing a closure, we pass a spore, right? And the spore looks like a closure with an additional header. So the header essentially specifies the captured variables, right? So in this case, what we're capturing is whatever the sender is, right? Storing that in this from, and so that's now fixed at the time when the spore is created, right? Because remember that all this code here is executed immediately, right? It's just that we're defining computations that happen asynchronously, right? But for example here, the spore will be created immediately, right? So as soon as the spore is created, this sender is actually fixed, right? So that's one way to fix these things. But of course, well, this is currently not automatically done. And if you want to enforce that, you would have to enforce that all the future combinators take spores, for example, instead of closures. That's a non-trivial transition, right? If you have you have all the issues with backwards compatibility and so forth that you have with languages like Scala and Java and so forth, right? So it's not trivial, but well, again, there could be possible refactorings that tools can help with, right? Okay. Good. So let me conclude here. Essentially, the point I was trying to make is, right, that concurrency libraries actually present quite a number of challenges for development tools, right? And they're not actually addressed, at least not. Some of them are addressed in the Scala community, but certainly not all of them, or many, or most of them are not addressed, right? And perhaps other language communities have different approaches, but there are definitely things that are low-hanging fruit, but there are also major challenges, right? And one thing that I think could be interesting is, can we improve the interface between library implementations and tools, right? And well, in Scala, we've sort of already started doing some of these things, very small steps. And in fact, this implicit not found example, that was actually just one example. There's another example also in the futures library that is another usability feature where users are prevented from calling certain methods in certain contexts where it's not actually safe. I haven't shown that, but there are ways in which you can improve the usability and tooling, I think, if you improve this interface. And well, this proposal I had in the middle is, of course, just a very modest, thought. But I think this could be expanded in quite a few ways. Yeah. So thanks for the attention, and happy to discuss.
So, any questions?